So I believe where we finished up on Friday, we were talking about polypoly capacity, right? And that's not in the notes. Okay. Did I ever remember to upload that handout that we were looking at the other day that had all the parameters for the different capacitances between layers, area, fringe, and all that kind of stuff? I did do it or I didn't do it? We're going to use it again today, which is why I'm asking about it. So I'm going to pull it up. And go down to the last page here. All right. I will need to upload that for you guys. You can. All right. So let me circle back around to what we're going to. Okay. So I would like for us to determine the capacitance of poly 2 capacitor if the poly 2 plate has dimensions of 20 lambda, 50 lambda, or a lambda is equal to 300 nanometer P5 process. And then I want to know, how does bottom plate parasitic capacitance compare to the desired capacitance value. So before we calculate things, we are only given the area of the poly 2 plate. Do we need the area of the poly 1 plate based on our SCMOS design rules? We talked about some of them last week, right? So the SCMOS rules say that the poly 1 plate has to extend beyond the poly 2 plate, right? So the poly 2 plate is going to be the limiting factor for our area of overlap. Yes. So for our poly to poly 2 capacitor, we are going to have, I'm about to sneeze. Maybe not. My capacitance per unit area figure for poly 2 multiplied by the area of our plate. That's going to be 20 lambda times 50. And then here will be, let's see, 0.3 microns quantity squared. So when we look at our figure here, poly to poly 2 has a capacitance of 893 attofarads per micron square. That is a very, very large value, right? So this is 893 attofarads per micron square. Another thing that I want to point out here, if we look at fringe from poly to poly 2, no value is given. All right. I want to see. Yeah. So there's no fringe capacitance given for poly 1 to poly 2 in the tables, in the textbooks table either. I think, I don't know for sure, but I think the reason for that is because since the poly 1 layer and the poly 2 layer are so physically close to each other, right? They're only tens of angstroms away from each other, that it's very likely that the area capacitance overwhelmingly is larger than the fringe capacitance, right? So much so that the fringe capacitant effects are either too difficult to measure, which probably means that they're too small to matter. Okay, so that's the logic I'm going to go with for why we don't have to include fringe effects for these guys. But I honestly don't know the exact answer. I just know the data isn't provided either in any textbooks or in the actual data provided by a fabrication run. So if we plug in this number, 893 attofarads per micron squared, what we wind up getting is a capacitance of 80.37 femtofarads for our intended capacitor. For our parasitic capacitor, that's formed between the poly layer and the substrate. And so we'll still have that area, but now we're looking between poly and substrate, whatever that figure is, and then we're going to use the exact same size for our plate. 20 lambda times 50 lambda. When we look at our table here, so between substrate and poly, we have 86. Right? Yeah, between sub and poly, 86 attofarads per micron cubed. Excuse me, per micron squared. Which gives us, okay. All right, so sorry, I have made a mistake here that's going to require us to look at our SCMOS rules to explain what's going on. Let me find. Poly 2, that'll be the easier thing. Nope. Next. Probably 11. Poly 2 for capacitors is probably where we should be at. All right. So our minimum poly overlap, we look at 11.3, right? What does that mean? Smallest dimensions, the smallest possible dimensions of our poly 1 layer are. So if our poly 2 layer is 20 by 50, and our poly 1 layer needs to overlap that, excuse me, our poly 1 layer needs to overlap the poly 2 layer by 5 lambda in all directions. So that means it's going to be 10 lambda larger in length and 10 lambda larger in width at an absolute minimum, right? So that means our dimensions here shouldn't be 20 times 50, right? What should they be? 30 times 60. When we substitute in that 86 attofarads per micron squared with that increased area, we wind up getting 13.93 femtofarads. And we can see then that our parasitic capacitance divided by our intended capacitance is 17.33%. So that means the smallest possible for this 20 lambda by 50 lambda capacitor, right? So 80 femtofarads. This is, I believe, it's been a hot minute, but significantly larger than the capacitors that we did with our metal layers early last week, right? I think we were hitting something like 45-ish femtofarads, and the plate size was pretty large. We're able to make our plates much smaller here because we're using, you know, the dielectric gap of the between the two poly layers, which is very, very small, but we can see that our bottom plate capacitance, even in this case, is significant. And the larger we make our poly 2 capacitor, the more and more bottom plate capacitance we're going to have as well, right? Because we're making that area larger every time. All right, so one of the things that we talked about on Friday was the voltage and temperature dependence of our N-well region's electrical behavior, right? So we saw how the resistance changed as a function of both applied voltage and due to temperature. And we can kind of understand why the capacitance changes as well due to voltage and temperature for an N-well piece of material, right? It all has to do with that changing profile of the depletion region. Well, a poly capacitor also, its value also depends on applied voltage and temperature. Any thoughts as to why? Temperature is probably a little bit easier to understand here. Any thoughts on why capacitor value would change due to temperature for a polycapacitor? So that's a pretty reasonable assumption, and that might have, that could absolutely have something to do with it. I don't know what the temperature coefficient of expansion for silicon is off the top of my head anymore. When I used to teach MSc 502 on the regular, and we were talking about using silicon as springs and thermal transducers and all that kind of stuff, I knew it then, but it's been several years. That's not what I'm getting at here. So what is poly? What am I referring to when I say poly? Polycrystalline silicon, right? Which is still a semiconductor material that's been doped. So it should fairly stand to reason that it's going to behave roughly the same as the N-well, just a little differently because it's more heavily doped, right? So what I mean by that is when we're using polycrystalline silicon for the plates of a capacitor, we're not using that, we're not using it as an intrinsic material. We're using it as an extrinsic material, meaning that it has been doped significantly so that it is a good electrical conductor. Well, we know that for a semiconductor, the mobility, which isn't going to play nearly as much of a part here, depends on temperature. And we know that the carrier concentrations also depend on temperature. We talked about that in our last class meeting, right? So this is where another place where the temperature dependence on our charge carrier concentrations can come into play here, right? Because as our temperature increases, we have more charge available to be stored in our capacitor effectively. So it's going to make it slightly easier to put charge on each plate depending on what the capacitance is, right? So we know capacitance is a ratio between charge and applied voltage. Well, if there's more free charge available to move to the plate, stands to reason that the capacitance is going to change for a specific voltage. So capacitance of a poly 2 capacitor varies with temperature and applied voltage. So the temperature relationship, C as a function of temperature, is the capacitance at T naught, room temperature, times a factor of 1 plus TCC, where TCC is the thermal coefficient of capacitance. Multiplied by T naught minus T. This thermal coefficient of capacitance is approximately 20 parts per million per degree C. And our voltage relationship is C multiplied by V naught, our average value of our applied voltage, just like it was for our N-well resistor, times 1 plus VCC, which is the voltage coefficient of capacitance multiplied by V minus V naught, where V is the difference in the plate voltages, so it's the total voltage drop over the capacitor. And we can observe or measure for our C5 process that this value VCC is approximately 10 parts per million. So my question to you guys, how do these coefficients compare to what we saw for N-well parameters? If I'm not mistaken, for N-well, we were using something like 8,000 parts per million for one, and I think around, it was either 1,200 or 2,400 or something like that parts per million for the other, right? So I would argue here that 20 parts per million and roughly 10 parts per million are significantly smaller, which means our poly and poly 2 regions are much more insensitive to variations in both temperature and applied voltage, right? So effectively, there's a lot of different reasons that justify the cost of having this second poly layer available to us for a particular technology node, right? We get a larger sheet resistance value if we have our high Z poly 2 layer available to make resistors, right? It's roughly 25% larger resistance than our N-well region. It's less affected by changes in both applied voltage and the operational temperature. It gives us significantly larger capacitance values for a significantly smaller chip footprint, right? So lots and lots of different reasons why we might like to include that second polysilicon layer. All right, let's see. The next thing I have is about metal capacitors, which we have actually talked about a bit previously. So I think I'm going to skip a lot of this stuff. This is what happens when I decide to teach things in a slightly different order. But this is something that we have not talked about. Okay. So we saw when we did our examples using metal capacitors that, again, our bottom plate capacitance tended to be on the same order of magnitude as our intended capacitors, right? So how do you guys think we could potentially mitigate that? Any thoughts? We can't move our metal one layer any further away from our bottom plate, right? So if we wanted to make a large capacitor that didn't have as large of a parasitic capacitance, we could make it between metal layers 2 and 3. That's a fairly obvious solution, right? Because the distance between metal layer 2 and the substrate is significantly larger, which means the plates are further apart of that parasitic capacitor. We are going to have some metal one involved in order to send our signals down to the rest of our chip and all that kind of stuff. But we can minimize that. But another really interesting way to do it is to utilize a stacked capacitor. And so what I mean by that is, let's say that we have wiggling so much. So let's say that we have our substrate. We have our insulation layer where our two poly layers exist, right? And then on top of that, we have our region where metal 1 hangs out. So let's say that we put a region of metal 1 here. Like so. Let's consider this guy right here to be our boundary where metal 2 sits. And I don't recall what color I was using for metal 2. Does anybody remember? Well, I'll just make up a new color. We're gonna call it green for today. That doesn't look green. And I'm going to put a little chunk of metal 2 over here on the left as well. And now, obviously, one layer up, I have access to metal 3. And I'm going to put another little chunk of metal 3 right here. So what I can do, let me label that as metal 3. What I can do I can put in a contact, or actually this would be a via 2 because it's between metal layer 2 and metal layer 3 here. Another via 2 region. And if I put one down here, it would be via 1. What I get is multiple capacitors, right? So there's going to be a capacitance formed between the overlap, bless you, of metal 2 and metal 3. And there's going to be a capacitance formed between the overlap of metal 1 and metal 2. And then I'm going to have a parasitic capacitance here between metal 1 and my substrate. How are the capacitances between metal 1 and metal 2 and the capacitor between metal 2 and metal 3 electrically connected? They're in parallel, right? If we consider the path down this left-hand side here through those vias, those stacked vias and all that kind of stuff, to be an electrical conductor, and it absolutely is, then we have stacked capacitor, right? So we're minimizing the footprint on that bottommost layer so that we should get a relatively small capacitance. In parasitic capacitance in comparison to the intended capacitance here. So let's say, just for the sake of argument here, or might not have enough room down here at the bottom of the page. No, it doesn't look like I do. So let's say, just for the sake of argument here, that the area of overlap, A, in all of our cases is 100 microns squared. All right. So that means our C metal 2 to metal 3 value, if we look at our guy here, we have some capacitance between, let's see, metal 2 to metal 3 is 32 attofarads per micron squared. We're going to multiply that by 100 microns squared, right? We also have a fringe between metal 2 and metal 3 of 52 attofarads per micron. So what's our perimeter? 400 microns, right? So in total here, we get 24 femtofarads. That seems. Oh, I see what I did. Sorry, I did 100, but I didn't square it. It's 100 by 100. Oh, no, that's not. Sorry, my brain is not in it today. What I mean by this is 100 microns by 100 microns, because if I didn't tell you that, there's no way to get the perimeter based on the area value. My apologies. Being a total and utter unorganized jackass today. There we go. This makes more sense. 340.8 femtofarads observed between the metal 2 and metal 3 layers. Between the metal 1 and metal 2 layers, let's look back at what we have over here. So between metal 1 and metal 2, we have 33 times that 100 squared. Between metal 1 and metal 2, we have 47 times that 400. And so we wind up getting 348.8. Femtofarads for a total capacitance of 688.8 femtofarads, right? If I added those, no, that's not even 689.6. I did the mental math in my head very, very poorly. For our substrate, so this is our parasites, right? It's formed between the metal 1 layer and the substrate. So technically this guy should be a little bit larger because we know that there's actually a little bit more area of overlap, but just as a kind of rule of thumb thing here, let's look at what this guy's going to be. So between our substrate and our metal 1, we have 28 attofarads per micron, so 28 times 100 squared. And then our fringe from substrate to metal 1 is 51 times 400 is going to give us 300.4 femtofarads. So it's on the same size, right? This parasitic between the metal 1 layer and our substrate layer is on the size of these stacked layers, but the more layers that we can stack up, the more we can see that capacitance rise and rise and rise without a corresponding increase in our bottom plate capacitance, right? Okay, so we've talked about variations in resistances, variations in our different capacitances and all that kind of good stuff. Let's finally circle things back around to some transistors. All right, so here are some of the problems that we can face and things that we need to take into account when dealing with MOSFETs. So let's say that I have a MOSFET and it is defined by this polysilicon 1 region and this active region. Right? As we draw our MOSFET, these are the two parameters that we really have control over, right? So we have ink here. Control over our channel length, ostensibly. and we have control over our transistor width. And from a top, excuse me, that's a top-down view. So from a side view, our expectation is that we have something that looks like this, right? So we have a very thin insulating gate layer. And then a very well-defined active region occurring on either side of our gate. There are going to be two things that are going to mess with this. Okay, mess with this nice and easy picture. Lateral diffusion and oxide encroachment. Okay. So what lateral diffusion means is that when the source and drain regions of a MOSFET are implanted, some portion of the implant dose laterally diffuses underneath the gate poly. So what we would actually observe is that instead of having this nice rectangular profile, it might look something more like this. It'll kind of round off, and some of it will be out underneath, and we should see that we'll actually have swelling on the other side too, but it doesn't really matter quite as much. So what does that lateral diffusion do in effect? Anybody have any thoughts? So there is conductive material below a conductive plate. So yeah, there is gonna be some small capacitance there, but that's effectively lumped into the gate oxide capacitance of the transistor itself. What is it doing to the dimensions of things? I guess will be an easier question to ask, and is really what I want to know. Exactly right. So we have this tiny region right here that I'm going to call L diff. So our length is getting smaller. So we see that lateral diffusion causes the length of the, or actually effective length increase as L effective will now be our drawn length L minus twice L diffusion. So why does this diffusion occur? Anybody have any thoughts on that? So what we've done, okay, to this point, the processing step here is our polysilicon layer has been deposited on top of our gate oxide, right? We have that very thin layer of gate oxide grown. We deposit polysilicon on top, and then we deposit some more oxide kind of over the surface of everything, and then do a photolithography process to etch away the polysilicon in places that we don't want it to be so that we just have our gate left over. The next thing we do is that we use the active region to cut a hole, or the active region patterns, where the hole in that field oxide layer is going to be cut to allow us to place our implants, right? And then we use the select layer to actually target things. So we are firing a beam of ions straight down over the entire surface of this wafer, and they are penetrating regions that have regions of the substrate, right? Our P-type substrate on other side of our gate. Our gate then should prevent anything from getting down underneath it because it's a physical impediment to that happening. All right. When does when does diffusion occur? This is a very, very basic question. Doesn't that, if I'm talking about the diffusion, let's say that I sprayed a cologne or something right here next to me, right? What does that diffusion mean? Over time, people in the back of the classroom are going to smell it. Why doesn't it stay right next to me? Exactly right. It wants to move from a region of high concentration to low concentration, okay? So if we have a very abruptly defined place like this, where we have a very high concentration of, let's call this an NPN transistor or an NMOS transistor, so that we have a very high concentration of donor atoms abutted next to a lesser concentration, significantly lesser concentration of donor atoms, right? Or no donor atoms except for atoms, because we're in the P-type region. We should see that diffusion at a minimum wants to occur. But now let's consider what happens when we're doing further processing steps and we're growing oxides and all that kind of stuff like that, right? What do we do to grow an oxide on a chip? We place it in an oxygen-rich environment and we heat it up. What do you think heating the chip up is going to do to the chances of diffusion? Increase it significantly. That's why we get these troughs and stuff underneath, right? So we have a perfect condition of, we want it to be real nice and neat. It wants to move in areas that has a lower concentration, and then we expedite that process by heating things up, okay? it's not necessarily a bad thing at all, right? This actually makes it, our threshold voltage smaller, helps making our strong inversion conditions happen also are increased. So, and we get a slightly smaller technology than we wanted. It's not necessarily a bad thing by any stretch of the imagination. It's just something that is happening and going on here. Now, it could be a bad thing if we were to let it completely run rampant, right? Like if we allowed enough diffusion to occur, so if we heated things up for long enough and at a high enough temperature, we could force those two areas of regions to effectively connect to each other. So what we have to wind up doing is putting implants in place to stop it. All right. So what happens, this is a fairly modern thing that happens. Let's say that I have a large region of chip space like so, right? And here's my poly layer. Excuse me, not my poly, my insulating layer over kind of the whole shebang here. And I'll put some undoped poly here and some undoped poly over here. I'm trying to form and well, excuse me, a PNP transistor on this side. This guy right here is N-well. So if I put in an incredibly highly doped region here, do the same thing on the other side. Right. So I put in a thin, excuse me, but extremely highly doped region. So like if my implants would be considered N plus and P plus, these would be plus plus. So they're even more heavily doped, but it's a very thin region. And then I effectively expose that same area and implant ions. What's going to happen is that my normal dopant implants see those incredibly highly doped implants and say, well, since that's a higher dopant concentration, can't diffuse in that direction. So you just get that little bit of help underneath each edge of the polysilicon layer from those extremely highly doped implants, which cause that reduction in threshold voltage and then in turn help strong inversion happen more easily. Or I guess those are really two kind of ways to say the exact same thing, but you don't see that your channel length winds up changing appreciably, because the diffusion of that very, very tiny layer, in order to make it spread wide, would require a very, very high temperature kind of situation, which doesn't exist, right? So you're doing extremely, extremely high doping in my bright color region, but you're not letting it really sink down very deep into the substrate itself. It's practically done just at the surface and a couple of angstroms down. Right. And so those are called, let's see, spacer implants, and they allow that. All right. All right, we got 15 minutes left. Let's talk about oxide encroachment. So I'm going to copy this guy right here over. So oxide encroachment what does the name imply? Let's start there. So if this whole thing right here is surrounded, right? So we've cut, I'm trying to think of the best way to explain this. So we use our active region, like I said earlier, to cut a hole in the field oxide, right? Oxide encroachment is really kind of just a misalignment problem here. So if like we don't cut our hole large enough, the effective width of our transistor gets smaller. Another way to think about this is float, right? So all of these patterning steps that we're doing in all this, like we don't actually have any super critical control of the dimensions that we're getting because it's all based on chemical processes, etching processes, and we understand the statistics and probability of what we're doing, but we don't have any finite control over the actual dimensions of these things that we're doing. So oxide encroachment is effectively, well, if I let my oxide grow for 30 seconds longer than I was supposed to, that can have an appreciable effect on the amount of stuff that gets cut away when I'm trying to pattern my implants, okay? And so what winds up happening is that we wind up the oxide layer accidentally overreaching or encroaching into our active region so that we have this very small dimension here called W. All right, that's causing the width of our transistor to be slightly smaller than it was drawn for, where our effective width, W effective, simply the drawn width minus twice the encroachment length. So how do we compensate for oxide encroachment? We make our active region slightly larger than we need it to be. Right, so what is the current voltage relationship for a transistor depend on, regardless of whether it's in the saturation region or the triode region? W over L, right? So, or at least that's what we have control over, right? It's going to either be twice or 1/2 or 1 mu times Cox. We don't really have any control over mu. We certainly don't have any control over Cox. W over L times some voltage squared crap, right? Depending on which voltage we're looking at and whether we're in the triode region or the saturation region. So this lateral diffusion and these oxide encroachments can skew that current voltage relationship ever so slightly. In a digital circuit, doesn't particularly matter. In an analog circuit, as long as we don't let things get wildly out of control, that's really not going to make that big of a difference either way. Like we're talking about having a channel length of, so in our C5 process where the minimum length of the gate is 2 lambda, that's 600 nanometers. We might be dealing with 595 nanometers instead of 600, stuff like that. When we're dealing with our width, right? So I think the minimum size, I think it's technically 5, but probably the smallest that we'll ever draw for anything useful would be 10 lambda, because 10 lambda is going to get us 2 contacts, so that if something happens, we don't break the transistor automatically. If there's only 1 point of contact, that means anything that goes wrong makes it fail. So having it 10 lambda wide or 3 microns wide allows us 2 points of contact, or two spaces to reach the contact layer so we can get signals on and off of it. But I mean, we're still talking on the order of tens of nanometers of encroachment that we're dealing with here. So in the grand scheme of things, for a very, very large process like we're designing for, these guys effectively don't mean a whole heck of a lot. If we were designing for a very, very small transistor, so short channel processes, these things would be huge, huge, huge deals to deal with, right? 5 nanometers doesn't mean a whole hell of a lot when you're looking at 600 nanometers, but 5 nanometers could mean an extraordinary amount when you're dealing with a 14 nanometer process. So your gate length is 28 nanometers by design. So anyway, we're 9 minutes early, so I'm gonna shut up now, and then we're gonna talk about parasitic resistances and all kinds of interesting goofy stuff tomorrow. Deal more with MOSFETs. And I think I might have lost my notes on common centroid design, so I'm gonna have to redo those.